So the first session is on fundamentals of computational fluid dynamics, and in this workshop we'll also touch up on the few simulation of the ANSYS Fluent, but like half of the part will be simulation in ANSYS Fluent and like basic simulation, and the first half will be fundamentals, and then the second half will be like some basic simulation in ANSYS Fluent. And in the next session and in the upcoming session, we'll go towards more multi-physics and more complex simulation, which includes complex meshing. I think everyone can see my screen.
Yeah.
Okay. So in this we'll study the fundamentals of computational fluid dynamics. So the basic steps in CFD solution in ANSYS Fluent. So if I show you the workbench in ANSYS workbench, so this is how a simulation in ANSYS works. So the basic layout of ANSYS Fluent is like this. First we create geometry, then we have mesh, then we set up the simulation like simulation parameter, boundary conditions, and what kind of algorithm we are using to solve, and then we move to solution, like we run the simulation and then we post process the result. One second, this problem. Sorry for this, guys. Now we'll start and we'll not stop, and I'll try to finish by time. If you have any question whenever I'm trying to explain, please stop me and ask. This is the basic layout of how simulation goes in ANSYS Fluent, and this is basic layout for each and every CFD simulation that we see. So here basic steps are same in every software, whether it is ANSYS, OpenFOAM, or COMSOL. The basic steps are same. First, we have pre-processing in which we make geometry, then we make mesh. In mesh, we have grid generation and quality. We have to ensure mesh quality also. Then we define the boundary condition. So the most important steps in CFD is solver setup, and as well as in ANSYS Fluent. So in that also we have first we describe our fluid properties. But the main important step is selecting the solver. So on the right you can see a image of solution part of the ANSYS fluid, in which you can see there is pressure velocity coupling is selected and the algorithm is coupled. So there are other algorithms also, such as simple like piezo, pimple. There are a lot of other algorithm also as well. So which algorithm to use? Okay. Then there are gradient approximation. So and then there are for pressure, they are using second order scheme, and for momentum, they are using second order of wind. So what are these gradient schemes, pressure and momentum scheme, and why are they so before running an ANSYS simulation, you should have a basic idea of what are the various schemes that we can use and what is their importance, and then what are the various solver option. And when you're running the simulation, then you should have the basic idea of how to choose your time step. What is CFL number? And these are the things. If you are very beginner to CFD and ANSYS, then these are the things first you should have idea of what are they. So this session basically cover these aspects. So so the simplest problem in CFD is fully developed flow in a channel. So why it is simplest? Because it can be because we have here a momentum equation in radial coordinates, right? And if we apply the scale analysis and for fully developed flow, we have but that in fully developed flow, we assume that the gradient of velocity in x direction and the transient terms are zero. The every term on the left hand side is zero, and the pressure, that is del p over del x, is constant. Like for a fully developed flow, it is always a constant. So if we use these, then we get this equation number 2. And if we do simple mathematics and integrates, we get the parabolic velocity profile that we have, and we all know this. If we include some more complexity in the equation, although this 2D heat conduction equation is linear, alpha is diffusivity here. The 2D heat conduction, although these equations are linear, but they can be like complex to solve. But there are analytical methods and some power series and Fourier methods through which this equation can be solved. Okay, so in for 1D transit heat conduction, power series solution are also available. So in power series solution is also approximate. So how many number of terms that you are adding is will determine how much accurate your solution is. So most of the time in Fourier and power series, we have to go till like 8 or 10 number of terms that will give us a good approximate solution. So, so for this kind of a complexity, we have analytical solution, mathematical solution in terms of power series or direct analytical solution. But if we increase the complexity of the problem, for example, if we in, add an advection term, so if we add an advection term in the heat equation, that is this ux del t by del x, uy by del t by del y. So along with conduction and transient term, if we add this convection term, then things get complex. We can't solve this using simple analytical or power series solution, and even separation of variable solution is not available for this. So this can't be solved by analytical method. So whenever an equation is not can't be solved by analytical methods, we have to go for numerical method. That's where the numerical methods comes in. So for example, so what we do in numerical method? So what we do is the above partial differential equation that you see, we discretize these equation using such that we approximate the gradient. Okay, so del t by del x, del t by del y, and these all things will be approximated in discrete form. So on the right hand side, you can see ij. So what we do, forget the right hand side. So what we have is we discretize using finite difference method. So the transient term, that is del t by del t, is
Excuse
approximated
me.
like this.
Mhm.
Yes.
Sorry, Abhishek, to interrupt you, but we are not understanding anything because these equations are very new to us. And since we all belong to different fraternity, we don't understand this terminologies which you are using, delta T, delta X, like something. So can you give us what are those equations and why we are doing this?
Okay, okay.
Like
So
del
I'll
T by,
go with
so it's, yeah, well, I'm like,
understood,
I'm
understood.
not
So
getting anything to be frank. Yeah.
all right,
Yeah,
all right,
same
all
here.
right,
None of this
all
is
right.
familiar.
So this is basic. Okay, okay. So all right, I'll go slow then. All right. So you understood this that these analytical solutions are there. So this is 2D heat conduction equation. So the left hand side is the transient term, and the right hand side is diffusivity, and the right hand side is diffusivity as well as the conduction term. I
My
think this
first
heat.
question, excuse me. So my first question is, what is computational fluid dynamics means? Why we are using this? First question is that. Before getting into the equation, I would like to know.
Okay, okay,
I
okay. So
really
I'll have to
don't
go more
know
slow.
exactly.
All
Yeah.
right, all right.
Yeah.
So
Go
yeah,
for
You
that's what
like
slow.
you
we
are
I
don't
think
know
asking.
the
it's about,
basics only.
yeah, we don't know the basics. So I think you
Terminology
can
is
start
All
from
basics,
there.
right, all
exactly.
right. Okay, okay. So I'll go with more basic. So what we have is, so this you understood, na steps in CFD solution? No. Okay.
Yeah, see,
So
step is fine. Like, it is the same in for every software. Pre-processing, post-processing is there. We have to draw
all
a
right,
diagram, then we have to give some for loads and all those things. Then we'll go for the post-processing. What are the results? That is very basic. But what the importance of this in CFD? Like we didn't got anything till now. What
understood.
are we doing exactly?
So I'll go very slow. So if you have any doubt, so the what I'm trying to say here is so this is momentum equation for incompressible flow in radial coordinates, the one equation one. All right. So in this momentum equation, what
Okay,
you will have
Abhishek,
usually.
sorry. Abhishek, sorry. I don't think any
Mhm.
of us, we are all civil engineers and architects. We don't know momentum equation, incompressible flow. I think these are all your mechanical terms. So maybe you
This
can
is
just
fluid
tell us
dynamics
what is
terms. Yes.
ANSYS. Yeah, so we are all civil
It's
engineers
fluid
and
dynamics we
architects.
wrote read in like 2015 or 16. Now it's 24.
Okay.
So
Okay.
maybe
Okay.
you
We
can just
don't
start by
use much.
explaining what is the ANSYS software and what we use it. And
Okay. All right. So, so actually, I made this PPT that took a lot time. So okay. Okay. So no problem. So I'll skip the mathematics part, but I'll tell you the basic things that are required. So I'll skip the mathematics part. Okay. Mathematics is seems complex, but it is okay. No problem. Understood. So I'll like first I'll get you through the basic slide that we have apart from the mathematics. What are the important aspects? I'll take 10 minutes and then move to the ANSYS. Okay. Is that fine?
okay, yeah.
Okay. So the basic, the fundamental thing in I'll this is important because for example you are using ANSYS normally it is okay. So but whenever you'll get any error, then you'll have to find then you may find yourself in a bad spot. So for that aspect, you should have a fundamental idea of the basics. So first important thing is domain discretization. So you have any domain, let's say 2D or 3D domain. You divide those domain into grids, meshes. All right. Then the second thing is variable approximation. That is the red zone is control volume. So whatever the value in this red zone is of any field UVP, it is considered constant as a center, at a center. Then we have discretization equation. All right. And then we apply the boundary condition. So, so discretization equation is basically is done by Taylor series. I'll not go into that. So, so in ANSYS, I'll just open the ANSYS for you. will take time. So the thing is, in ANSYS, if you have to select some things, for example, hello, let it open. We look the methods here. So this is the most important part of ANSYS, that is methods. You can see you have a simple algorithm, simple like piezo and coupled. And if you go to these schemes, the pressure scheme, you can see standard, presto, linear, body force, vector, second order. And if you look at the momentum, you have first order of wind, second order of wind, quick, and third order, these schemes. And for energy, you have the same. So if you are solving any complex problem, you should have an idea what are these, because you may have to change your schemes based on the problem that you get in your simulations. So basically, these schemes are nothing. So these are like forward difference, backward is central difference. All right. So I'll share my this slide with you. If you want to read, you can read, but you should have basic idea what are these schemes. So this is more on the fundamental side. The upwind scheme is, for example, if you are so I'll just explain you the basic difference between the simple and piezo algorithm, which is important. So in simple algorithm, what we do is simple algorithm is for steady state. So whenever you have a steady state, so this is the algorithm. First it solve momentum, then pressure correction, then velocity correction. And then if the solution converge, it will stop, otherwise it will go again. And in piezo algorithm, so there is a piezo loop and there is a next, so it will go to the next time step only when the piezo loop in converge, and it is used for transient, it is used for transient simulation. So this is enough from the, now I'll move to the ANSYS. So in ANSYS Fluent, you have analysis system. On the left, you can see you have fluid flow. So the I just wanted to you guys, you know that. So my part was to show you fundamentals of CFD, show you a little bit of coding, and relate that coding to the flow to the ANSYS, how ANSYS does it. So more on the fundamentals of ANSYS, how it work, like what are the various things that ANSYS is capable of, will be covered in the next session. So quickly, whatever I have prepared, I'll finish it, because you guys don't want a fundamental ANSYS part, like fundamental of
I
CFD.
mean, we are okay with learning it, but if you can explain it, that would also be fine. But we are not understanding the way you are explaining. That's what we meant. If you can explain it, but I don't think that much of
So
things we'll be
actually,
able to cover. It seems very a lot of
I thought that the momentum equation you should basically that much you understood. I understood. I thought that, but if you are not able to understand the momentum equation, then I think it will be a problem.
Is it a problem to use the software without understanding it, or
It is not a problem, but you should have a basic idea, because so if there
Yeah,
are
I
already
can you
benchmarks,
explain it? Can you explain the momentum equation?
yes, I can. Yes, I am explaining, but so for example, this is the momentum equation. When I'm saying this is the transient term, this is advection term. So this is pressure term, and this is basically diffusion term. So this much you have to understand. Otherwise, I can't. This slide basically covers every fundamental thing that there is in CFD. Most of them important things. So if you are able to understand this is
Basically,
transient,
we have to understand the fluid mechanics because this all terminologies comes under fluid mechanics subject, which we read in like 10 years back. So right now, like we didn't knew that you wanted us to know about all this incompressible flow and all those equations. It's not that tough to understand, definitely, but right now we are like lacking, like we are not in touch with the subjects. We never used it. So point is that because you are a mechanical engineer, you use it in your daily routine things, these things, but we aren't
yes, yes,
using that.
understood.
So if the thing is
Actually,
very simple from our end, it's like we are very basic. I am from civil
so
engineering,
So,
she is from architectural
like the
background. So
rest
it's
of you
very
also,
tough for
like who
us.
are there,
Yeah.
Even what I
yes,
feel
Praveen,
that,
yes.
yeah,
Ashwati,
yeah.
Shweta. Uh,
If
yeah, so my
So
question is, do you want to learn this fundamentals also, like go with Abhishek on the fundamentals? Or maybe like what I had done last year, I was using ANSYS. I had just gone to my mechanical friends and learned what we had to do without understanding the basics. It is hard without understanding the basics. So it's up
yes,
to the
yes.
rest of
So
you guys. You
it
can
what
tell.
it will be
what
hard. So in beginning it will not be hard, but
I
let me tell you what
I
will
would
happen. Because so
what I
what
feel
will
that,
happen is in if
excuse me,
can
what I feel that if you
uh,
start from the structural point of view, beam, column, if we go
no,
by
no,
that
this
way,
so that will be on last session. Na? So this is fundamentals of CFD. So the workshop
even
plan was already there. So in workshop plan, the
Praveen,
first and
yeah,
second,
we need to know the software before we get into beam column. That is much later.
okay,
It's not
yes,
STAD
yes.
or
So
anything. It's ANSYS.
okay,
Yeah.
fine. Then
so
even
what?
though whatever the gradient term is, that ratio, deba by deba u by deba t, you just
Mhm.
touch it. What is mean by t? T is time, u is um, initial velocity or final
All right,
velocity. In that
understood,
way, if you go,
understood.
then it will be fine.
Okay, okay, all right. So heat conduction equation everyone understand, I think. So heat conduction equation everyone understand, I hope.
Please
The
just
thing
explain
is,
the terminology. That is what is capital T.
all right,
So we can
all right,
correlate it
all
with.
right,
Uh,
all right, all right. So here we have a heat equation. So in a heat equation, so T is temperature, small t is time, x and y are the coordinates in x and y direction. So first term is transient term. All right. The second term is advection term. It is called advection because the flow field, that is u, velocity in x direction, ux, and velocity in y direction are taking the temperature with it. Like it is uh, uh, acting as a advecting mechanism for the temperature. So flow is moving in right direction. Let's say the temperature will also move in right direction. That is called advection. So here the transport variables are u and x, and the variable that is being transported is x, t. So this is called advection terms in transport. This is called advection term, and this is basically the conduction. Alpha is diffusivity, so this is conduction. So this is conduction term, and this is q is heat generation. All right. So I understood what you're trying to say. I'll go by using this. So this is basically transport equation for temperature, that is heat. So that is heat equation. So this heat equation, there is no analytical solution available by any of the method that I have described before. So when the equations get complex, they get non-linear. This is non-linear term. So when the equations get complex, we can't solve them by analytical methods. Then we have to go to numerical methods. So what we do in numerical methods, we approximate every term that is there here using a discrete point variable. So what we say on the right, we have like we have a center, a point at center, on the right, on the left, and the like right top and right bottom. We have like 6 points. So we have a domain where we want to compute the fluid dynamics, and we discretize those points by 6 points. So what we do is basically using these 6 points, del t by we approximate every gradient. So del t by del t is this. All right, is Tij, that is Ti. This is n plus 1 is the next time step, and n is the previous time step. So using this terminology, we discretize this. All right. So move ahead. So you understood more better from this. So for example, we have a 1D steady state heat equation. So this is 1D steady state heat equation. So what we do is we discretize that equation using this in the using various points. So I minus 2, so I is a point in the 1D domain, I plus 1 is another point, I plus 2 is another point, I minus 1 is the backward point. So we have points. So del t by del x will be approximated using t plus 1, this point, and minus ti divided by delta x. So this is the approximation for del t by del x. So this is when we take either we can use I plus 1 or we can use I minus 1. So when we use I plus 1, it becomes forward difference. When we use I minus 1 from the approximation, it becomes backward difference. All right. So basically this comes from Taylor series. So this approximation comes from Taylor series. I'll share the PPT and you can have a look. Then we have a in higher orders, like if you want to have second order derivative, then we have to include more terms. If we want to have third order, if you want to use calculate cubic derivative, we have to include more terms. So this is how we discretize things. So we discretize the domain, and from those domains we calculate the derivatives, first order derivatives, second order derivatives. All right. So this is a 2D steady state heat equation. So this is nothing. So we have conduction term. So we have del square T by del x square, but del square T by del y square. This is basic conduction equation. Conduction 2D heat conduction. All right. So conductivity is not required if there is only conduction to solve this equation. So using central difference scheme, we differentiate. So we approximate this del square T by del x square like this. All right. So this is how it gets. So you can go into the mathematics later, like you can take a copy pen and do it yourself. And similarly, we approximate this second gradient in y direction also. What we simply do in CFD is we put both like this or like this, and then so here is with heat generation. Here heat conduction equation with heat generation. What we do, same thing we are doing that I show in the previous slide. We approximate the gradients in discrete form. Then we put it like this. Simply we substitute these in above equation, the heat conduction equation. And then what we do is we keep Tij on the left and we push every terms on the right. And we solve this iteratively. Okay. And we get the solution. Similar for the transient term, similar thing we can do for the transient term. And we have some scheme like explicit and implicit schemes. Yeah, finite volume method. So the thing is, so this is the resulting equation, right? So we have to solve it. So I'll just show you quickly how it is done in code, and then I'll move to ANSYS and show it's the same thing in ANSYS Fluent. So this is a MATLAB code for steady heat equation. So what we have is Lx and Ly are length of the domain in x and y direction. So we have a domain like this. So we have a rectangular domain like this. We have length in x direction and length in y direction. So Lx and Ly are the length in x and y direction. Now what we are doing is we are dividing these lengths in 20 discrete points. So Nx and Ny are 20 discrete points. K is the conductivity. and Q is the heat generation. All right. So we divide these parts. So the grid size will be this. That is domain size divided by number of grid points. So this is how the loop looks like. So this equation, I'll share every material. If you like in future, if you want to have reference, it will be very easy for you to understand. So basically this is the equation. All right. So what we do in basic CFD is we solve this T new ij iteratively. So this is a Jacobi method. I'll simply run it and show you. So this is the loop which is also used in ANSYS as well, and I am also using the same loop. This is the solution that we are getting. So in here we have at left boundary we have temperature 273. On the right boundary we have this boundary condition, and these are the boundary condition on the top boundary. On the left boundary, this is on the right, this is on the bottom, this is on the top, and this is the solution. So whatever I've shown you in this code, I'll do the same thing in ANSYS. All right, we'll move to the ANSYS. So in ANSYS, we have on the left, we have analysis system like Fluent, CFD. So these are different analysis system. So we have IC engine. So this is only fluids part. If you want to do like mechanical things or different like electronic simulation, mechanical electromagnetism, then you have to install that also. So I have installed only the fluid part. So in the component system, you have geometry. So you can also make geometry differently. Okay, you have CFX. So these are different. These are design exploration. You can use more. So this is only the fluid part. So what I'll do is I'll generate a new system. Okay. So in this first you have to. So these are the various things that you can see here. You can also export a system from outside. You can also import a project from outside. So these basic things will be covered in next session. So my part is to show you the link between the coding basic CFD and ANSYS Fluent. So I'll open the geometry. What I will do is I'll make this geometry, and I'll implement the boundary condition, and I'll try to show you the same things using the ANSYS. So when you open the geometry, you have two options. First is you edit geometry in space claim, which is more advanced. The second is edit geometry in design modeler. So for the beginning, we should focus on design modeler because it is very easy to use. The space claim is like this. So you can see there are a lot of options in space claim: design, display, assembly, measures. So in the I think in third day, one of the guy will show you how to like do complex geometry, how to make complex geometry in space claim. But for this session, we'll only we'll go ahead with the design modeler, which is comparatively simple to use and is also fast. Making geometry is easy in this in design modeler. So this is a 2D geometry, so we don't have to. So we'll just make a 2D geometry first. One thing. First, you have to go to properties and you have to select You have to select 2D from here. Now it is, we have selected the 2D geometry. We'll open it with the design model. Okay, so quickly make this. So we'll make a rectangle, a sketch. Now we'll go to dimensions and we'll give it dimensions. So we'll keep everything as one because it is always, for fundamental simulation, you should always keep things as unity. All right. Now what we'll do is go to sketching, go to concepts, surface from sketches. We'll select this, or we'll select this sketch and we'll apply. And now we have to generate. So you can see we have the geometry is created. Now we'll move to the mesh part. So when you see this tick mark, when you see this tick mark,
Actually, is it better to create geometry in space claim or this?
so yeah, so if it is a simpler geometry, it is better to go for the design modeler. But space claim is has more features than a design modeler. So the next session will
Okay.
be like more on, as I told you, it will be more ANSYS focused only. So in that you can ask a lot of things. So my part was to conduct basic of CFD. So, but it is better to use design modeler for simpler domains.
All right.
So whenever you see a tick mark, so this is after geometry, there is a tick mark means geometry is updated. So now we have moved to the meshing. So in meshing, there are two things that we have to do. So first is simple, you do generate. All right, it will generate some mesh. It is generating some mesh. So what sometimes you have to refine it. So the mesh that we selected in this code, I'll also be sharing this code. So if you learn this much, so you'll cover the basics of CFD also. So in this code, we selected this the number of grids as 20. You can see 20, but here it is showing like 1, 2, 3. So it is lesser number of grids. So you have to provide. So you have to give edge sizing, insert sizing. So all right. So now you have to select where you want to give the sizing. So here are things that you can control. So this is to select a complete control volume. This is to select a face. This is to select an edge. All right. So you can select an edge. So you have to click here and select an edge. You can select all edges and then you can say apply. All right. Now edges are selected. Now how you want to do the edge sizing using number of divisions or element size. So we select number of divisions. How many number of division we want? 20. It should be same as the that we have in the code. So because we want to compare. So now after this we'll generate. You see, when we give S sizing, the internal domains, internal grids are not good. So these, although the every mesh is quad, so there are different type of meshes. Like some are triangular meshes, those are called unstructured, and some are quadrilateral meshes. So these are in like all are quadrilateral, and this is also unstructured, but this is quadrilateral mesh. So we don't want this. We want, because this is only a 2D domain. We want everything. We want a uniform structured mesh. So this is quadrilateral unstructured mesh. I'll show you. So this is not a good option to go with. So I'll delete this. So how we want to do is, so this, the length is 1. The length and width are 1. So what we will do is, in this, in the mesh options, in the sizing, we'll just growth rate, default size. So in the default, so this here in the element size, in the mesh option, we will select 0.05. All right, and then we will generate. You see, now we have the same number of bits as we have in this mesh, as we have in this code, MATLAB code. So now the mesh is created. So this is the mesh that we want. We can improve the mesh. If you want to do mesh independent study, you'll have to go from the courses to final mesh, because you want to see after what side of mesh there is no changes in the result. So for now it is just a basic case, so we'll go ahead with it. So now what we have to do is we have to apply boundary condition. So this is only 2D domain. So this is 2D domain, so we have to have only, so we'll have only boundary condition at the edges. In 3D you'll have to also apply boundary condition at the faces. So we give this as a left boundary, this as right boundary. So these are the two important tasks of the meshing. First is meshing the domain, and then defining the patches, or defining the uh, boundary condition, the faces or the edges for the boundary condition to be applied. This is bottom wall. This is top wall. So let's see. This is left wall. This is bottom wall. This is right wall, and this is top wall. And we can also, have selected this. One second. It is not coming as 2D domain. One second. So this is fluid domain. Mm. This is not- I think we should start from the beginning, because it is showing a 3D. Let's check it out again. Let's check. I think I have a doubt that it is showing us the 3D geometry. So we can check, always check from the, can always go to the properties here, and we can check. So analysis type is 2D. It is okay. We can always do this. We'll do generate, look at mesh, left boundary, bottom boundary, right boundary, top boundary. Yes. All right. So what we will do is we will generate here, and we can also update here. I think it's always best to update things here. So when you do update, it will be like this. You can see now the tick mark is here. It means that we can move to the setup case. So when you have a 2D case, the dimension option will not be here. You can see the 2D here, and we'll start it to launcher. Okay. So the most important, so you can see in Fluent you have domain in which you can also do little bit of like you. So when you import any complex mesh, you will have a lot of zones, you have a lot of edges. So in some of the cases you may have to combine the zones or delete them, or you may have to do little bit of rendering to the mesh.
Abhishek,
Or Mhm.
uh, can
Yes,
you
yes.
explain what do you mean by complex zones? Like, and what is the simple zone? What is
Okay,
the difference?
so
Like, right now everything is
yeah, so
looking
in this
complex to me.
okay, okay. So you understood how I made the geometry and the mesh, right?
Yeah, that I understood. Okay. But mesh size also we can change in this, or
Yes,
is
yes,
it
we
by
can
default?
actually the mesh size. I changed the mesh size. Now I like did little bit of things to show you the how can we can change the mesh. One second. So I show you here that these are the various things that you can do. So these things will be
Yeah, this
taught
is
in
fine. I
details.
understood your left wall, right wall. I understood your sizing of mesh. Okay, fine, fine. Got it. But tell me that zones wala thing. What you mean by
Yeah,
that
so this is
zone?
very simple case. So in this case, we have only one zone. So if you are doing FSI simulation or if you have multi, so this is only one zone because we have a singular mesh which is for continuous zone. So for example, so if you are using different cases like conjugate heat transfer or fluid structure interaction, or if you have a fluid flow through a channel, fluid flow through a canister or something like that, then in that case you may have different meshes zone which are connected through an interface. When two mesh zones are connected through an interface, then there is an interface for those zones and different mesh zones. So that will come later. That is a more complex part.
Okay.
So, but here we have only one mesh zone. So there is, you can see a continuous mesh zone. There are no two meshes, and the context between two is not there.
Okay.
So that will come. Don't worry. These things will come. This is just an introduction of the CFD part. Okay, so we have domain, then we have physics. Like we have to define physics whether the model is multi-phase, heat transfer is there is not. So for this we have heat transfer is there. And what kind of viscous model, Navier-Stokes equation, along with Navier-Stokes, what kind of viscous model we want to use. So you can use envisaged laminar flow, and these are the turbulence models. For now we'll only move with the laminar flow. This is only heat, we'll solve only heat, so even it doesn't matter we choose viscous or laminar here, turbulent or laminar here. So radiation is off, all these things are not required. So next important thing is define a material. So here material is by default air. So so in this you can have different materials. So you can go to the Fluent database and you can take the properties of a lot of materials that you want. You can see a lot of the materials are there already. So you can also always give any take any give the value to materials which are not in ANSYS by directly giving here. All right. So you can also define the properties here, constant, ideal gas, and you can at the end new input user defined. You can also like input the value of property using the user defined function, which we'll cover in the next session in the second half of the day. So it is air, and then we have solid. Okay, so because this is simple heat conduction equation, there is no need for this. So we have already have a fluid in the cell zones. We have only one zone. You can see there, that is surface body. So as I tell, where when there are different kind of mesh and different zones, you have to sometime define here. So you can also like edit this and define the properties of the cell zone. So you can have a porous zone, 3D fan zone, embedded LES, and different kind of things you can define for your zones. Then we have boundary condition. So we have internal wall, which is this. The boundary condition for this is not required because this is internal wall. So we have to define the boundary condition at the bottom wall. So bottom wall momentum is stationary wall. So there is no momentum. And there is, so this is only heat conduction. So we'll not give any velocity boundary condition. We'll only give temperature boundary condition. So if we look at our MATLAB code, so on bottom we have 273, on top 373, left is 223, and right is 348, and these are in Kelvin. So we have, this is bottom wall. So we have 273, apply constant wall boundary condition. So left wall is left wall is 323, right wall is 348, right wall is thermal temperature, this is left wall, bottom wall, (373). Maximum temperature is on the top wall. Okay, now the boundary conditions are applied. So now the next thing is we have to do is we go to the methods. This is, we use only simple algorithm because this is a steady simulation, and these will keep at this. So there is no need to change for now. So whenever you have to change this, the ANSYS will provide guidelines, and he will provide that which is a good pressure or momentum schemes for your case. But sometimes you have to juggle with these things. In control, we'll go. These are relaxation factor. So when your simulation diverges, you use those relaxation factor. But here we have only energy. So when your solution is not diverging, you don't need to give these relaxation factor. These are only case when your solution is diverging. It is, so for example, it is the value is going in millions or trillions of any parameters. In that case, you have to give a relaxation. You can also give relaxation to body forces, momentum 0.7. Next, we'll go to run calculation. So in the general thing, we have pressure. So we give steady simulation, and we are in 2D space, which is planar. You can also have axisymmetric. So the simulation is not transient, it is steady. There is no time in it. So simulation will start and it will give us a steady state solution. So there is no input need to give a time step or the initial and final times. in run activity, because this is steady simulation, so there is no time step needs to be given. It is only how many iteration you want to go. Let's say 500. And what we'll do? Okay, we have to initialize the solution. You can always, the solution is initialized. So this is hybrid initialization. If you click on standard, it will ask you to compute from, you can all Jones, you can say let's compute from left boundary. So when we put this as left boundary, it will directly take that temperature and we can initialize it. So by default initialization is also okay. So now what we'll do here is calculate. You can see it is solving at it is calculation is complete, solution is converged. One more thing, in residual. So in this case, what we have given is, so to understand this, what is the residual? So residual is the difference between the two iteration. So for example, in fourth iteration, the difference between the fourth iteration and fifth iteration is less than 10⁻⁻⁶ in energy. The solution will stop and it will say the solution is converged. So you can see here, although I like ran simulation, number of iteration I gave is 1000, but at bottom you can see the solution is converged only in 5 time step. Because in this residual monitor we have given a residual for energy equation, that is temperature 10⁻⁻⁶. All right. So as soon as it, you can see here. So at 4 time step we have residual as 1.24 10⁻⁻⁶, and at the 5th time step it is converged. So as soon as these residual are achieved, the solution will stop. So you can also see here that for x, continuity x and y, we have residuals. You can also increase those residual if I increase it to 7. Okay, and what I'll do is, okay, and I'll rerun it again. It will again calculate, but now it will go, the residual will go till 10⁻⁻⁷. So these are the basic CFD parts, that between two iterations the error should be very small. That's the basic of it. So now the solution is converged. Now we'll have a look at contours. You can see here. So this is, if we do banded, it will show like this. Also enable the contour lines. So this is the solution that we are getting. Okay, and from the my code we also get the same solution. So color map is little bit different, but from the code that we get and from the ANSYS Fluent that we are getting is the same. So ANSYS Fluent is doing everything that is in, that you can look into this code. It is the same thing, but the thing is ANSYS Fluent only works on finite volume method, the fluid part. For structural part, there are different methods, discretization methods like finite element method, but ANSYS Fluent primarily is primarily fluid part is in finite volume method, because it by default makes sure the momentum and the conservation of fluxes is always there, like the momentum continuity, and these equations are by default conserved. So now we have run a simulation that is steady. Now we'll try to do a transit simulation. So what we'll do for transit simulation is, for transit simulation we'll give a heat zone. For the fluid, this is a cell zone, we have only one cell zone. What we will do is, will edit it, and in this cell zone we'll tick mark the source term. As the source term is tick marked, you will see something here, and in this will now what we are doing, 2D heat conduction with heat generation. Number of energy sources is 1, okay, and the value is constant. So let's give it 100. So we're giving a heat generation of 100. Okay, we'll select it, okay, and we'll apply it. Now extra thing that we have it is we have given a heat generation, and one more thing, you can always, like new input parameter, you can always use a user defined function for these cases. You can also, for nowadays in these versions, you can also use the expression, but UDF can also be inserted. So we have added a heat source of 100 watts per meter cube. Now what we will do is we'll go to the solution part, and then now before moving to solution part, we'll go to general and make the time as transient. As soon as you make that time as transient, there are a lot of other options that are there. For example, in residual monitors, if you go, so convergence condition, you will see here solution convergence or time step convergence. So when you will add time step convergence, what it will do, it will try to converge. So this convergence parameter that you have, so these convergence parameter will be achieved at every time step. So for example, in a time step, in a single time step, you have 20 iterations. So in those 20 iterations, in each these in the two adjacent iteration in a single time step, the ANSYS will try to achieve these convergence criteria. Otherwise, for time step convergence, otherwise in solution convergence, it will just do a fixed number of iteration and move to the next time step. So we are keeping it as solution convergence because it is very simple problem. We'll go to the calculation activity. We'll go to run calculation. Now you can see that when we ran a steady case, we didn't have this number of time step here. But now I am making this simulation transient. We also have a number of time step here. And you can always keep the number of time step as fixed or adaptive. So when you change the number of time step to adaptive, you can see it is either CFL based or error based. So CFL is basically so CFL is a number. So in transient simulation, you have to calculate delta T based on this CFL number. So for now, we'll keep it as fixed. We'll user defined, and we'll use number of time steps as we'll take 1000 time step, let's say, and we keep this as 0.01 time step. This is maximum number of time iteration in a time step. These are 20, and the reporting interval and profile update interval is only 1. So these are basically after how much after how many iteration you want to see the residuals. Okay, so now everything is okay. So let's calculate. One more thing. Auto save. So if you want to save your data in transient simulation, you want to save your data at different time steps. Like if you have simulation running till 100, you would want to save data after every time equal to 5. So let's say we have 1000 iteration, we want to save after 50. So save data file after every 50 time steps, or let's say after every time step. Okay. What we will do, we will run the simulation. You can see at every time step, the error is jumping and then coming down. So it is showing that so this is the showing the time step, that at the peak you show is start of the time step and the end you see is end of the time step. And we have set a convergence criteria for temperature as 10 raised to power 7. So it is resolving the convergence to till the 10 raised to power minus 7 time step. Let's stop this. Keep running. It is saying calculation is complete. Okay. Now what the changes that we have seen. So now let's see the contour part. Okay. So now the final assembly. So now results are changed a little bit because we have added a heat generation. Now if we try to add same heat generation. So this is the animation. So I'll run the animation. There are no frames also. Animation, we will see the animation here. Let's see. Just give me a moment, 1 minute break. I'll be back. So where were we? So now we have opened the CFD post, and what we will do is we'll make a contour. All domain location is symmetry plane. So symmetry plane 1 and 2 are both are the same. You can choose either of them. Select temperature. Let's number of contours as 20, and you see. All right. So heat generation has changed it a bit, but that there is not much of a change. Okay. So let's increase the heat generation and run the simulation again. And what we will do is, so heat generation that it gives a very large heat generation. The heat generation is very large now. Okay. So for to make the animation, to make an animation or to save the number, to make animation look how the temperature changes with time, to make that animation, what we have to do is we have to define a contour here. So in solution, first we have to initialize the solution. We have initialized the solution and convergence condition in residual. Let's change it to 5 so that solution is don't take much time. 5 is okay. In graphics, in results, we'll add a new contour. Save and display. Okay, this is the new contour. So this is the t equal to 0 time step, and we are adding it. Okay, save and display. And what we will do is we will add it to the scene. Create a scene, and I think we have a lot of contour. We'll delete these. Let's make it again. Save and display. You can see that, and now we have contour 1. Now we'll add it to the scene. What will happen is during the runtime, you can also, along with the, okay, so along when we'll run the simulation along with the convergence criteria, the residues, you can also see the simulation. So now what we have is we have increased the heat generation, and we have added a contour for the animation. Now, and we'll do everything as it is. We'll run it 100 and not to save date data file every time, so it is okay. And we'll calculate now. So this should give us a movie of the transit simulation also. Autosave is giving us trouble, so calculate. Let it run for some time. Wait for 5 minutes. You can see, so there is some problem with the animation. So that will be covered in next section. So you can see when we add a larger heat, you can see the contours has changed. A similar thing will happen in the code. Similar thing will happen in the code if we add heat generation, let's say 10,000. You can see similar thing is happening here. So I think the heat is little bit larger on that side. Okay. So similarly, I have a code. So these are the again. Guys, the thing is, my part was to cover the basics of CFD, and I think we should have floated a prerequisite form that to understand the basic fundamental of CFD, you should like learn, take a one day and learn these things. So my part was to show the fundamentals of CFD, then show a little bit of coding, and then the aim of this session, and then show that in the ANSYS workbench. How does this happens in ANSYS? But because most of you guys don't have like basics idea of CFD, so there is no point in like whatever I have done in this PPT and what I have prepared in MATLAB code. There is no point in showing that. And I myself is not that much of a proficient in ANSYS Fluent. I have used it, but I have not used in past like 4 years. So I'm ending this workshop here and right now because there is no point in wasting your time. So the time that we like I will not cover here. So the time that is left of the workshop will take 1 or 2 hours extra in another sessions. Like we'll take doubt session of yours only regarding the ANSYS Fluent. So I think we should end this workshop here and right now because these fundamentals of CFD and this coding part that I have prepared, you will not understand until unless you have some prerequisite knowledge of very basics of fluid dynamics, like basics of fluid dynamics and CFD. Any of you have any issue, so we'll take 1 and 2 hour extra in our next session. In the next session, not in next session, in maybe tomorrow or the day after tomorrow, we'll have 1 and 2 hours extra, maybe for the structural part or bending of composite materials. In multi-physics part, we'll take extra hours of our will present for extra hours. I think it is okay if anyone has any question issue, then he can let me know. Because there is no point because these are the very basic things that anyone will teach you in the next session or more complex problems they will teach you. I hope everyone is okay with this. Yes, yes.
So who is teaching the next session? It's not you, right? Who's teaching?
It's not me. So this is Abhishek Gupta. His PhD is only my PhD in coding. So my master was in ANSYS, but my PhD work is in like coding part. So the another guy that he will be taking his PhD is he's working in ANSYS Fluent from past 4 years.
Okay. So he'll be the one taking tomorrow's session.
Yeah, tomorrow's session also, the day after tomorrow's session will be from one of the alumni who is working in a company and he works in fluid structure interaction and multi-physics simulation. So his whole PhD is also in ANSYS. So what I was thinking is I'll teach you the basics. So we can also take a class on this basics again, like 2 hours, but I'll have to give you some materials to study like prerequisite to these basic coding and
Yeah.
basic CFD part. I think that is required because I have made this PPT very understandable if you have little bit knowledge of like momentum equation, continuity equation, heat conduct, e-
So when I
any
started
variable
learning
transport equation.
ANSYS, I was taking help from two other mechanical PhDs. They were telling me that when you do BTech in mechanical itself, you get into a lot of these things, in fact, which gets applied
Yeah, yeah,
later
yeah.
in ANSYS. So like
Yes,
we
yes.
are
So
all
even
BTech in civil or
mhm,
BArch, so we have absolutely no connection with it. So what they told me was rather you just follow the steps. This is what you want as an output. This is what you do. But the problem
so
with that,
they
what happened is later when there was any issue, every time I have to
mm,
contact them because I am not able to
yes, yes,
understand. So that's why it's also important to understand the fundamental part of the working of
yes,
ANSYS.
yes. So at least you should understand that the variables that you are using in setup part of the ANSYS, what are they? Like what are the
Yeah.
schemes? What is simple algorithm? What is piezo algorithm? So I have made this PPT to show that only. If you look at the last part, I'll take just
Okay.
5 minutes more
Shweta, you
to.
have some question? Shweta?
So here I've shown you the piezo algorithm. What is piezo and what is simple? Where piezo is used, where simple is used, like the basics, very basics. Yeah, yeah. Go ahead, please ask questions. You are not audible. Your voice is too low. Not yet. Vishnu, are you able to hear her?
No, no, it's very low. Shweta, volume kuch problem? Okay.
So what I do is, I'll do one thing, Vishnu. I'll share this code and PPT
Yeah.
with you. So you
Hmm.
you guys can take like 1 day or 2 day. You can understand what is the prerequisite required, and will study for 2 3 days. And after that, I can go through this PPT and this code line by line, and take a 2 hours session because
Okay. Is there
there is no
any
point.
maybe YouTube links or something that we can also use to understand things?
So the thing is, YouTube
Like the
material is
basics
always
part,
available.
because the basic part, because
Okay.
like I said, हाँ,
Mhm.
बैचलर से ही हमने
Understood, understood.
छोड़ दिया.
Understood. So actually, if this is a board to board conversation, I can teach you on the board, then that will be better. But here in online mode, there are restrictions also, na.
Hmm.
So I'll share the content that is required for the prerequisite. And if you guys are comfortable, I'll take a 2 hour session on this, like how this is, what are these codes. These codes I
Hmm.
wrote like during my CFD course, like 2 or 3 years back. So
Okay.
So I'll share the prerequisite content, and if you guys agree, I'll again retake this session. And only the coding part, basic fundamental coding part, and how they are implemented in ANSYS Fluent.
Okay.
So Shweta is asking something.
Question would have come up.
Sloshing will happen. Yes, sloshing is part of FSI, na. So it will be covered more and less. So
Yeah,
we'll
we have
cover the
shared,
basic.
Shweta, and everyone has given what they wanted that I've shared with Abhishek. He has included it in day 3, if I'm not wrong.
Yeah, yeah, fundamental of sloshing as well as FSI multiphysics simulation, like thermal and structural combined, then thermal, structural, and fluid combined, one-way, two-way coupling, everything will be covered in third session. So next session will be taken by Abhishek, and he'll teach you guys uh, like basic simulation, how to run it, how to make meshing, complex meshing, tetrahedral, and all these meshing, and then he'll show you how to insert a UDF for boundary condition, for cell zone condition, all these things.
Yeah.
Okay, then we'll end this here, and because there
Okay.
is no more.
Yeah.
Yeah, I'll share the content
Okay.
on
Then we'll
WhatsApp.
leave it.
We'll
You
see.
can
Yes,
share this recording also. Yeah.
I'll share the recording as well as the content that I have, like PPT and code.
Okay. Okay, Abhishek.
Okay, okay.
Thank you.
Thank you, everyone. See you in the afternoon.